Hello everyone, I am Eugenia Kalnay. Today I will give an overview of our work on data assimilation and ensemble forecasting over my career with my students and colleagues. This is an outline of my talk today. I will briefly start with my education and my appointments over my career. Part 2, ensemble forecasting and breadth vectors. Part 3, ensemble Kalman filter development. What 4D bar can do, ensemble Kalman filter can do as well. Part 4, ensemble forecast sensitivity to observations, EFSO, and proactive quality control, PQC. Part 5, carbon and coupled data assimilation. I want to start with my education and employment over my career, where we developed the methods in this talk with my colleagues and students. I am originally from Argentina and started my education at the University of Buenos Aires under Rolando Garcia. I got my PhD in meteorology at MIT in 1971 under Jules Jarnet. I was the first woman student and the first woman professor in meteorology at MIT. Then I was branch head of the global modeling and simulation at NASA. Then I was director of the environmental modeling center at ENSEP in NOAA. Then I was Lowry Chair professor at the University of Oklahoma. And for more than 20 years, I have been at the University of Maryland, and I will be retiring soon. We will first discuss the ensemble forecasting, predictability, and breeding methods. The problem of ensemble forecasting is that given limited computing resources, we need to create an ensemble of about 100 members representing the uncertainty of high-dimensional atmospheric evolution. At NMC, Zoltan Toth and I, in 93 and 96, developed the breeding technique to generate the perturbations for ensemble forecasting. The breeding cycle is very similar to the data assimilation cycle, but because it evolves with the data assimilation cycle, it captures the error evolution of the atmosphere. At that time, our focus was on synoptic scale weather. Then, when I started working as a professor at UMD, my students and I started to expand the breeding technique to study a wider range of topics. With my student Matthew Hoffman, we first derived breadth vector energy equations. The breadth vector energy equations have many advantages compared to linearized equations. We then used these equations to study the instabilities of tropical Pacific currents. With my student Steve Braybush, we extended the application of the breadth vectors to the Martian atmosphere and used it to understand the instabilities of the Martian atmosphere. We found that topography plays an important role in determining favored locations of near-surface instabilities on Mars. With my postdoc Min Kai, we tried to use breadth vectors to study the ENSO signal, and we succeeded in using breadth vectors to detect the El Niño signal with a Zibia-Kane model. One limit of this model was that this model filters out fast timescale instabilities. So our next question was how to isolate the slow ENSO mode from other fast modes in a coupled system. To isolate slow modes in the coupled model, my student Malaquias Peña and I found that we can use a longer rescaling interval for breadth vector calculation so that the amplitude of the slow signal is comparable to the fast mode. To test if this idea worked, Peña and I created a coupled Lorentz system that mimics the real coupled atmosphere ocean system. This system has an ocean component, a tropical atmosphere, and an extratropical atmosphere. It can also generate the ENSO-like signal. Through our experiments, we found that changing the rescaling interval allows us to isolate the signal of different modes. With a short rescaling interval, we can get the instability of the atmosphere. With a long rescaling interval, we can get the instability of the ocean. By contrast, it is difficult for the singular vectors and Lyapunov vectors to get the slow modes of the coupled system. After successful experiments on the toy Lorentz model, we shifted our focus on real coupled model applications. My student Shuqi Yang and I successfully isolated the ENSO signal using the NASA coupled model. We also found that the ensemble forecast initialized from the Brel vectors captures the ENSO signal. Very importantly, with my student Matteo Corazza, we demonstrated that Brel vectors show spatial structures similar to the background errors of the day for data assimilation. Using a quasi-geostrophic model, we showed that the background error covariance constructed from only 10 surrogate Brel vectors can explain over 85% of the background errors. My student Yongjing Zhao showed that Brel vectors can be applied to study the instability of rogue waves, which is important for wave modeling. Besides these applications, my graduate student Adrienne Norwood compared Brel vectors with other ensemble forecasting methods. Recently, we made some new progress on coupled system forecasting. My graduate student Eviatar Bach used Granger causality analysis to determine the major driver of predictability. He confirmed the findings of the Kalnay dynamical rule, which says that the atmosphere drives the ocean in the extratropics, while the ocean drives the atmosphere in the tropics. In addition, my graduate student Eviatar Bach also developed a new approach to predict oscillatory signals. Essentially, instead of directly forecasting the whole physical space, we can first project into an oscillation subspace and make easier predictions there, and then convert the signal back. During the early stage of the development of the ensemble Kalman filter, my students and I made strong efforts to make ensemble Kalman filter competitive with 4D bar. We showed that what 4D bar can do, ensemble Kalman filter can do as well. My student Takemasa Miyoshi really made a crucial contribution to the widespread adoption of the LTKF invented at the University of Maryland. His dissertation is among the first that demonstrated that the localized version of the ensemble Kalman filter is better than 3D bar using low-order models. He also created a realistic data simulation test bed with SPEEDY, now frequently used to test new data simulation ideas. More importantly, he made all of his LTKF codes open to the whole data simulation community. Now, LTKF is very widely used around the globe. At that time, the most advanced data assimilation method was 4D bar. There are 4 components that make 4D bar powerful, which I listed in this slide. First, as a smoother, 4D bar can use all the observations in the assimilation window, so it spins up fast. Second, it also uses outer loop to handle the nonlinearity from the model. Third, to reduce the computational cost, 4D bar can adopt different resolutions in its inner and outer loops. Last, the weak constraint formulation of 4D bar allows including model bias in its formulation, which significantly improves for the 4D bar performance. To make ensemble Kalman filter as good as 4D bar, my group developed the equivalent 4 components in ensemble Kalman filter, as we will see in the following slides. We found we can apply the same weight obtained from the current data assimilation cycle to its previous cycle. The more detailed proof can be found in Brian Hunt's 4D ensemble Kalman filter paper. Essentially, this property of the LETKF gives us a no-cost smoother, allowing us to get improved analysis for free. With my student Shuchi Yang, we took advantage of the no-cost smoother and developed the running in place method and the outer loop method for the LETKF. The experiments with toy models show that the LETKF combined with these 2 features is as good as 4D bar. Experiments with state-of-the-art models also show that the effectiveness of the running in place algorithm, especially when quick model spin-up is needed or when observations are sparse. For example, Shuchi Yang showed that assimilating observations with the running in place algorithm can reduce the Whorf model spin-up time significantly and can improve the prediction of tropical cyclone structures. My student Steve Penny used the running in place algorithm to extract abundant information from sparse ocean observations and generate a more accurate ocean analysis with the ocean model MUM. More recently, my postdoc Yun Liu applied a modified running in place scheme to the GeoChem model to reduce the mass imbalance problem introduced by the ensemble Kalman filter for the carbon data simulation. 4D bar reduces its computational cost by using coarse resolution in the inner loop. For the LETKF, the most computationally expensive step is to conduct eigenvalue decomposition at each analysis grid. We then developed a method to reduce this cost in the LETKF. Instead of repeating eigenvalue decomposition at each analysis grid, we can first calculate the LETKF weights at coarser resolution grids and then interpolate the weights to the full resolution grids. With Shuchi Yang, we showed that even with 2% analysis grids, weight interpolation can generate analysis with similar quality from the full resolution analysis. By contrast, the direct increment interpolation instead smooths out the small-scale features and severely degrades the analysis. Starting with my student Chris Danforth, we developed an approach to conduct low-dimensional model bias estimation. With my graduate students Hong Li Yan Zhou and Kriti Bhargava, we further included this model bias estimation components into the LTKF framework and showed improved analysis and forecast with toy and operational models. We also developed an approach to assimilate observations with non-Gaussian errors into the LTKF. To examine if this method works, we applied it to real observation precipitation assimilation. With my student Guoyan Lien, we showed that assimilating trim TMPA precipitation with Gaussian transformation improves the NCEP GFS global forecast up to 5 days. This improvement is seen on almost all the variables. With my student Cheng Da, we showed that assimilating GPM-based GSM AP precipitation improves typhoon track and intensity forecasts for almost 3 days. Another important data assimilation work in my career was the development of the ensemble forecast sensitivity to observations, or EFSO for short. In 2012, I developed a simpler formulation of the EFSO so that it can be used for all types of the ensemble Kalman filter. Essentially, EFSO can quantify whether each observation improves or degrades the forecast, and by how much they influence the forecast. I will show some basic applications using EFSO. For example, with Yoichiro Ota, we show that EFSO can quantify the impact of each type of observation assimilated into the NCEP GFS weather forecasting model. With my students Zechun Chen, we also show that we can create an online monitoring system based on EFSO, so we know when the analysis degradation occurs. With my student Zechun Chen, we show that EFSO can also be used for channel selections, which is extremely useful for hyperspectral infrared sounders, since these sensors usually have more than 1,000 channels. With my student Guoyan Lien, we showed how to use EFSO results to develop physical and statistical quality control procedures for new type of observations, such as trim TMPA precipitation. Assimilating TMPA precipitation with the EFSO guided quality control improves the model forecasts. With my student David Groff, we showed that we can even predict EFSO values without assimilating them, which prevents the forecast degradation due to the assimilation of unqualified new observations. In addition to the basic application of EFSO, we advanced it further. EFSO can identify which observations degrade the forecast. One idea was that we can redo the analysis by not assimilating those flawed observations. Then the forecast should be improved. We named this procedure Proactive Quality Control, or PQC. With my student Daisuke Hota, we showed that proactive quality control with modest wins can improve the forecast using the operational NCEP GFS model. With my student Zechun Chen, we developed several formulations of proactive quality control and compared their performance using the low-order Lorentz model. We found that among all the formulations, the formulation that reuses the gain matrix K shows the best performance. So for PQC, we do not need to recalculate the gain matrix in the LTKF, which further reduces the computational cost of PQC. Continuing with Zechun Chen, we tested the revised PQC algorithm with a low-resolution NCEP GFS model. In the experiment, we separated the total correction of PQC into accumulated and immediate correction. Our experiments with the GFS model show that most improvements come from the accumulative correction. More recently, my student Chuchun Chang extended EFSO to an ocean model and got very encouraging results. She developed a density-based norm for ocean observations and implemented EFSO in the ocean model MAM4 inside the CFS version 2 LTKF. She found that the largest positive impacts of L4 SST observations appear in the regions with the largest climate variabilities and also in the regions of tropical cyclones. She showed we get improved ocean temperature and salinity forecast for the upper 200 meters by rejecting the detrimental ocean observations. In the last section, I will talk about my work on coupled data assimilation, because I believe that this will be a very important topic now and in the next decade. I will start with my work on coupled atmosphere carbon data assimilation. In 2011, with Ines Fung and my former student Jisung Kang, we started to work on carbon data assimilation. For carbon data assimilation, we developed the variable localization technique to improve the carbon flux estimation. The idea of this method is to zero out non-zero ensemble error correlations between physically irrelevant analysis variables. Though simple, this method is very effective and significantly improves the carbon flux estimation. With my postdoc, Yun Liu, we found that applying the running in place algorithm to the carbon data assimilation also improves the carbon flux estimation. In 2011, my student Tamara Singleton and I started to work on coupled data assimilation with a low-order coupled atmosphere ocean model. We compared both ensemble Kalman filter and 4D-bar on their abilities to constrain simultaneously the fast and slow modes of the coupled system. We found that these two methods are comparable for coupled systems. With Tamara Singleton, we also compared the ocean analysis accuracy from two types of 4D-bar systems. One is strongly coupled 4D-bar with a coupled model. The other is echo-like 4D-bar with a forced ocean model. The results show that echo-like 4D-bar shows smaller analysis errors for model states than the traditional 4D-bar. But echo-like 4D-bar using the forced ocean model is still inferior to a strongly coupled 4D-bar using a fully coupled model. In addition, the echo-like 4D-bar cannot improve the flux estimation. Later, my student Cheng Da developed a coupled data assimilation testbed for a coupled quasi-geostrophic model. This package includes all state-of-the-art data assimilation methods under different coupled data assimilation strategies that allows a comprehensive comparison. For both 3D-bar and ensemble Kalman filter, the strongly coupled assimilation approach generally shows smaller analysis errors than the uncoupled or weakly coupled approach for both atmosphere and ocean. Unlike 3D bar, the ocean analysis from the strongly coupled ensemble Kalman filter is substantially better than the weakly coupled ensemble Kalman filter, a feature not observed for 3D bar. Cheng Da also compared all strongly coupled approaches for all data assimilation methods under different observing networks. Many interesting results are obtained in this study. For example, under a full observing network, strongly coupled ensemble Kalman filters and 4D bar show similar performance better than 3D bar. The outer loop coupling is as good as strongly coupled 4D bar in this scenario. When only the atmosphere is observed, ensemble Kalman filter is better than all variational methods. The outer loop coupling approach performs the worst among variational methods. My graduate student Travis Sluka compared the strongly coupled and weakly coupled LETKF with an intermediate complexity global climate model. We found that strongly coupled approach not only improves the ocean analysis, but also the atmosphere analysis. Our real observation experiments with the CFS version 2 LETKF show similar results. Strongly coupled LETKF improves observation fit for near-surface atmosphere variables, but it degrades the fit under the ocean mix layer. This degradation is probably due to the spurious error correlation estimated by small ensembles. To mitigate the issue of spurious error correlations, my student Takuma Yoshida and I developed the correlation cutoff method to remove unreliable error correlations between irrelevant variables. We developed a simple rule based on the Kalman filter equation. We should only assimilate observations of which ensemble perturbations show strong error correlations with the updated variables. Experiments with the coupled Lorentz model show that the performance of the strongly coupled data assimilation varies significantly with the ensemble size. However, the strongly coupled data assimilation with the correlation cutoff method always shows the lowest error, proving the effectiveness of this method. We then thought about how to extend the correlation cutoff methods to realistic models. The correlation cutoff method requires us to obtain the localization function for each model state observation pair. My student Takuma Yoshida developed the neural network approach to obtain those functions relatively easily. We first tested the neural network approach on low-order models, and they worked very effectively. For the 4 toy error correlation models that simulate correlation between geopotential and winds, the neural network predicts the value and sign of error correlation correctly when verified against true values. In addition, the error correlation of zonal winds predicted by the neural network shows similar structures as those acquired from the NMC method. We then applied this approach to an intermediate complexity model and found that strongly coupled LETKF with the neural network-based correlation cutoff method shows very encouraging results. Both the atmosphere and ocean analysis are improved globally. Okay, this is the end of this talk. I want to give many thanks to all of my students and colleagues without whom I couldn't have done this work.